Here is a key idea. Before I get to that, so let me mention. As going nowhere and running it backward, and then running it is the same as that, so that would correspond to this. And then we will have laws like refl p is p, which is p refl, and you have to fill everything in to make the types all work out, but that's the gist of it. What other group laws do I want? Groupoid laws, and I want to know like associativity. So PQR is PQR. And then we spent some time talking about what does this mean, because the really cool thing is that these are equations, and so the equations are themselves paths in another space, another identification space. So we get these iterated identity types. So these kinds of things tend to take place, in general, these are of the flavor P is equal to Q in a type representing some A is equal to B. The shape of you have to write down the exact details for every one of them, but they generally are talking about paths between paths. So we had a picture like this. For example, I didn't draw this one last time, but I'll do it this time. We can have A, B, C, and D, let's say, and we have paths here and here and here. And then we have this structure, which is we can compose those paths to form here. That's one composition. We can form a composite path, which is here. And then I can compose this with that, which is here. And then I can compose this with that, which is here. And then the associativity law says that this is a face, that there's a face here. That these two outer edges, which represent the two compositions that I'm given here, one can be deformed into another. Okay? So that's the sort of picture. Do you see the idea of the picture? Or if I get rid of the interior clutter I have between A and D, what I have are two separate paths from A to D given by these associativities, and then there's some higher path which relates one to the other. And of course it's invertible, so really I could draw these with double arrows if you want. Okay, but we can think of it like that. So it's invertible. So the idea is that there's a deformation which can take us from one to the other and backward. And so this is what we mean by the groupoid laws. And as I mentioned, these are the groupoid laws can be written like that. And then it's all a question of what we mean by equality. So these are, if I only demand, the weakest possible thing is to say, well, whenever two things are supposed to be equal, what I really mean is there's a proof, there's a piece of evidence that connects them. Okay? That is an element of this so-called a higher identity type. Okay? We could call this somehow a higher identity, or sometimes we'll say that the equations are true up to higher homotopy of paths. Okay, path homotopy. So when we have these iterated equality types or identification types, that gives rise to this higher dimensional structure. Very quickly, like now at the next stage, if I iterate that one more time and talk about paths between paths, it becomes difficult for me anyway to draw them. Okay, I don't know how to draw those very well. So you stop relying on the drawings and you start relying on the algebra. And in a sense, that's what algebra is for taking you to dimensions that you can't really depict, that you can't really draw or visualize very easily. So the idea is that this structure continues, so to say, to infinity. That is, I can do identity types of identity types of identity types of identity types of identity types, and it's like that all the way down. Okay? And the sense in which the groupoid laws holds the most general sense is the idea of a weak infinity groupoid. That's what we talked about last time, a weak infinity groupoid. That's really what I'm doing. And weak here means holds only up to higher homotopy. The other possibility is if you just look at this kind of a picture, you might have seen before, for example, in category theory, and you might have seen that instead, in category theory, the demand is that these equations hold, so to speak, on the nose. That this be the exact same mapping. This mapping, if you think of these paths as kind of mappings, we're saying that this mapping, this is the analogous thing in a category, is a composition of mappings. So if we have this composition and we have that composition, we demand they be equal, but equality in that sense, in the usual strict one category sense, demands that they be identical, that they be the same. So that's where the notion of weak and strict comes from. So it's a question of how we interpret equality. But in type theory, equality is interpreted by these identifications, and so the natural world in which we live in type theory is to treat things weakly or up to higher homotopy. So that is a sort of a brief summary of where we got to last time. We got as far as talking about the weak groupoid laws, and now I want to say more things that are necessary to make everything else in the theory make sense. So what I want to talk about next, so that's the picture to remind you. I think that's all I wanted to do by way of recap. Let me just check. I said to myself, draw the associativity diagram. Okay, so I did that. Okay, and then, okay, so I know what we're doing. All right, so the next thing I want to talk about is revisit this issue of what initially I called functionality, which will now become generalized to functoriality. And that's what I want to get at. So what I want to talk about right now is the notion of functoriality. So what I'm going to do here is I'm going to use the elimination rule for J for the identity type, which is called J, that I developed last time. And we developed that elimination rule on the basis of thinking of it as of the identity as an inductively defined type. So let us remind ourselves in informal terms so that we know. We can do it formally and formally and informally. So formally, we have the following elimination rule to remind ourselves. Given two endpoints and some path between them, I want to say something, we'll call it P, about that data. Okay? So that's an element of U. That's a family of types, but it's or you could say it's a relation or predicate, depending on how you feel like speaking at a given moment, or a family of types. But I can think of it, if I try to think of it propositionally, which is what motivates the thinking of this as an induction rule, I want to say something about an arbitrary path between arbitrary points in the space A. Okay, so that's what I want to do. And in particular, what I want to say is I want to say something about a particular path. So I have a P around here, which says that A and B are equal, okay? And I want to say, under what conditions, okay, can we say that there's a proof that P holds for A, B, and little p? So we want to give the conditions for that. And what we developed last time was the idea is it's sufficient to consider reflexivity. The idea is you say, well, for any x in A, please exhibit for me little p, and I'll write of x to stress it, which says that the property holds for x in refl. And then if you can do that, we use something called J here, and then there are various notational conventions. So one way we write it is we write that of x dot p and OP. Sorry about that. I overloaded here. Let's call that one Q. Okay, and Q. Okay, so that's what I meant to say. And that was the data. And we have the property, just to remind you, that let me just write shorthand. If we do x dot p in refl, if you really run it on refl, then that's definitionally equivalent to A for xp. So that's the formal thing. So informally, we call this principle, we call this path induction. We're going to use path induction several times in a row here right now. So I want to say something about path induction. So this line, this thing here is called the motive for the induction. That's the terminology. Okay? So the motive for the induction is the relation you're considering. Let's call it a relation for the moment. There's the relation you're considering on, that is defined on arbitrary path in a space A. So we want to say something about it. That's the so-called motive. The second thing is the particular path in question. So this is our path in question. Because in the end, what we want to know is something holds about that particular path. Okay? And this part, okay, what did I call that? I had a terminology I was writing here. Oh yeah, this is the sufficiency or something. So we can look at this as sort of the inductive step, if you want to look at it like that, okay, which is written here, or it's the sufficiency. It suffices to show the following thing. If we wish to show that this holds for an arbitrary path that we're considering, then it's sufficient to show this. Okay, so that's the sufficiency. And if we have those three things, then we can conclude that the property holds, that the motive for the induction is valid for that path. So I can write it informally as the motive is valid for, I'll just write Q, but I mean A, B, and Q, because you have to specify the parts of where Q goes from. But let's just say Q brings A and B along with it. Okay, so we're going to do a lot of proofs, or several proofs, and then later we'll, when Dan takes over, we'll do a lot more proofs that will follow this pattern. So this is the pattern of path induction. We're going to do this a lot. So the reason I write it like this with a chart like this with the correspondence like this is because at the end of the day, you know, very often we'll write a proof, we'll say, okay, theorem something or other, which is the motive, and the proof will be by path induction. And really the theorem is the property of interest. And then what we do is we choose a motive. That's often the trick right there. And then what we're going to do path induction on some path P, whatever P might be, you pick that in question, and then do the reflexivity case. And then you say, okay, we're done. Okay? And the idea is that what goes in this data is ultimately writing a functional program using a J somewhere in there, which gives us the property we want. So every time we're doing a proof, we can write it math style if we want, that's fine. But when you pull it back along these correspondences and make it precise, so if you were mechanizing the proof and you really have to instruct the machine, you know, quite explicitly, what you're doing is you're writing a functional program, and you're often working by computing with J. Now, I'm going to come back a little bit later to a remarkable thing about this. But okay, so now here's what I want to do with this notion of functoriality. So the general idea, remember that functionality, informally, what did functionality mean? It meant that everything, well, this is very loose, but you know what I mean. Everything respects definitional equivalence, or definitional equality. So for example, if A is definitionally equal to B, then, and I have a function, I'll say that FA is definitionally equal to FB in B for any F which goes from A to B. That was for example. Okay? Because, you see, the definitional, this is what we mean when we say that everything respects equality or respects definitional equivalence. This is what we mean by functionality. Okay? So it behaves like a function. So a function cannot distinguish definitionally equivalent arguments. And if we think informally, the definitional equality expresses equality of sense or some kind of just simple calculation, it corresponds to the idea that you can't define a function that is one thing on 2 plus 2 and something else on 4. Okay? Otherwise it wouldn't be a function. Okay? That's the whole idea. Okay, so you want to say we can respect the calculation or definitional equality. And a related one, which really comes out as a special instance, is we know that, again, A equals B in A implies, okay, that capital F of A is the same as capital F of B in U, this is a particular thing, for a family of types F, which is A to U. So this is why I introduce universes, because this is really a restatement of that with a particular choice of B being U, that's all. Okay? That's the convenience I mentioned before. So when I have universes, it becomes convenient to catch these two things the same. Now, we also pointed out when we first talked about functionality in this form, the grass pollen must be increasing. When we talked about the functionality in this form, we pointed out that definitional equivalences, being mere calculations, they don't give us a lot, right? This doesn't, we use this quite a bit, but it doesn't give us as much as one might guess naively. So we talked about the famous example of sort of x plus y and y plus x as natural numbers, expressions of type nat. They are not definitionally equal, and therefore these principles don't apply. Okay, so what the functoriality is going to express is that everything respects propositional equality, or we could say homotopy. So what I want to say is, for example, the following kind of idea. I want to say if A is equal to B in A, this, under the same assumption that f is such a function, then f of A is equal in B to f of B. But this statement is much beefier than it looks, because if you look at it from an ordinary conventional mathematics viewpoint, this is just, equality is treated as a proposition, either holds or it doesn't. And you say if A is equal to B, then f of A is equal to f of B, and it's like yawn, okay, what's to say about that? But no, the important point here is what we're really going to be saying is something about the space of proofs. What we're really going to be saying is, when I write this, I mean, that's true. So I say, if you give me a proof that A equals B, then I can turn that into a proof, which in this case I'll call app. And if you want, there are different notations, but one thing might call app FP, which is a proof that f of A is equal to f of B. And the important thing about doing proof-relevant mathematics is this is where the action is, okay? Where the action is in writing down and characterizing the proofs that exist and understanding what are those proofs. So this thing called app can be read in two ways. It can be thought of as standing for path application, or it can be thought of as the action on paths. So for those of you who, and this is now this motivates for me the idea of functoriality. So if you're familiar with the idea of a functor in category theory, it's really it comes in two parts. If I have a functor, I'm mapping from one category to another. There's the F, let's call it F. We have F0, which maps the objects of the category A, let's say, to the category B, and then a corresponding function F1, which maps in A into maps in B in such a way that certain coherence conditions hold. That is, it preserves composition and identity, typically on the nose. So it's the same thing here, is that when I write F of A here, right, so you can think of F of A is sort of zero cell application. What do I mean by that? A zero cell is a point, okay, in a space. So if I wanted, I could call that app0 F of A. Apply F to A in the sense of a zero cell, okay? And then I need another notion of application, which I'm writing app-fp here. And sometimes there's some notational thing about what to do, but the idea is that sometimes it's written with banana brackets, okay, or what I've written over here is, I've also written that as app-fp, but if I were thinking of this in the most general way, this would be one cell application, but this would be to P, okay? So this is one cell application, which in this case is its action on morphisms or on maps. Okay, so a one cell can be thought of as an edge, it can be thought of as a map, it can be thought of as a morphism, okay? It can be thought of as a face, but it's a face in the same way that a point is a face and an edge is a face, and we can go on. And we can do these through all arbitrary dimensions. We can start talking about the dimensionality. So, but this is like in category theory, you have merely, in one category theory, which is the category theory you normally use. These days, people are very interested in infinity category theory, which is the analog of what we're doing here with type theory, where, for example, the coherence conditions on functors don't have to hold, so to speak, on the nose. That is, the functor applied to a composition doesn't have to give you exactly the composition of the map, but it rather is deformable. And what does deformable mean? It means that there's a morphism in yet another higher hum, There's a morphism between morphisms. So that's where we get this kind of structure as in infinity category theory. And these days, that's the way people think about category theory. Infinity categories are the case of interest, okay? Whereas historically, one categories were the things that got the ball rolling. Okay, so we have this notion. So this is sort of one cell application. So we can think of this as, here's zero cell application, and here's, but F of A is, when I gesture here, F of A and F of B are zero cell application. App, okay, is the one cell application, which says a function is also a functor that has an action on paths, AP, which when given a proof that the arguments are equal, that is a path between A and B, then the mapping will transform them. So if we take A here, and we take B here, so these are let me give these guys names. So these are A and B. Then if I look at what F does, okay, what does F do? It'll send this guy to A. It'll send this guy to F of B. That's the zero cell application. And moreover, it will send the path P to a path. Well, let me be loose here. Let me write F of P. That's a slightly abusive notation, and it can be very confusing. Once you have arbitrary dimensions, you never know where you are. So we have tended to shy away from that. But in one category theory, that's what you do all the time. You just write F of a, you know when you're using the morphism part of a functor, and you know when you're using an object part of the functor, and you just don't notate them the same way. But that notational abuse becomes not very helpful once we start working in the infinite dimensional case. And so I'll use this only very sparingly. Okay, but the picture is the path is transformed into the path. So here's another way of thinking about it. We're going to give an example a little bit later toward the end of this lecture, is we're going to have a space called I, which represents the unit interval. And it has 2 points, 0 and 1, and it has a segment between them. So if you take any mapping F that's going along here into any A, what is F going to produce? If I just follow this picture, what are we going to see in A if we take a function F from this scenario, this particular type, which I'll call I, which stands for the interval or the 0 circle, okay? We have the interval. How do we take the interval over, what does F do? What is going to happen here? Well, what it's going to do is it's going to produce a path in the space A. If you want to pick out a path in the space A, the way you do it is you define a map, okay, from the interval into A. Because what F will do necessarily, once I finish proving this functoriality thing, what F will do necessarily is it will, F of 0, the 0 application, will be the endpoints of the path. And then F of seg will be some path between them. And let me write it in a crazy way to sort of stress that F of seg is any path that you care to pick out between F of 0 and F of 1. So paths in a space can be identified with maps from I to A. And in fact, we're going to wind up with that. We're going to look at the total space of the identity type will be equivalent, in a sense I'm going to explain, isomorphism up to isomorphism. The total space of this, the big sum, will be equivalent to the function space I to A. And if any of you have ever studied any homotopy theory in classical settings, what you do is I is defined to be a subset of the real line, and a path is given by a continuous function from the actual analytic unit interval into the space. Because it says this really is the real number 0, the real number 1, and this is the sequence of points that exists between them, and then you have a continuous transformation. That's called analytic homotopy theory, because the starting point for it is you start with analysis. You start with the real numbers, and you start with the topology on the real line, and you work with continuous functions on the real line. And then you start building up the notion of path from there. That's analytic homotopy theory. What we're doing is what functional programmers would do. This is like assembly. If this were really the analytic interval, then it's sort of like assembly language programming. It's sort of like saying, okay, yes, if you really insist, you could build up all of the apparatus of, functional programming in C by just doing everything by hand, okay, in terms of memory management and moving things around and so on. And if you could stand to do it, you could do it. Yes, go ahead.
So when you say that F of seg is any path?
Yeah, it's any path. Well, what I'm saying is you can choose, if you want to pick out a path P, you can choose F, which is a mapping, which will be a mapping from I to A. We'll pick out a particular path P. Or the other way around is, if you give me such an F, what it's doing is picking out this path.
So it's deterministic?
Well, it's a function, yes.
Right.
Yeah, it's a function. Yeah, exactly, right. So it picks out a path. It's the idea that, it's the generalization of the idea that the elements of a set can be identified by functions from the singleton into the set. Every such mapping determines one element of that set, and every element of that set can be picked out in that manner, okay? Well, this is the generalization of that from 0 cells to 1 cells. Say if I can pick out 2 elements of the set, and what I'm really picking out is a path between them. And any path arises in this way. Okay, that's what I'm saying. So, yeah.
So what you're saying is this is the free path?
What's that again?
This is the free path in some sense?
Free path.
Free, like free algebra. Unique mapping to any path.
I don't think I mean that. I just mean it in the sense that I was saying that maybe there's a way to see it that way, but I'm not seeing it myself at the moment. The idea is that it's just a generalization that the elements of the set can be identified with maps from 1 to A, and so the paths in the set can be identified with maps from I to A. That's all I'm saying.
Yeah, so if there's a unique one for every path.
Yeah, for every path there is. Yeah, that's true. Because it's kind of an initial object in some way. Yeah, there's a kind of an initiality going on here. Yeah, that's true. I'd have to think about the right way to say that, but yes, you're probably right. Okay, it isn't, okay. So I want to finish a minor point, which is, so analytic homotopy theory starts with analysis. What we're doing is synthetic homotopy theory. We're doing what functional programmers would do. We'll say, look, the idea of a path is an abstract type, okay? And what I care about path is that there's a trivial null one, and there's a concatenation of them, and there's a reversal of them, and I don't care how you implement that in assembly language, okay? Like, it's not important to me what bit banging you do to realize that abstraction. What I care about is the abstraction. Okay, that's called synthetic. In this setting, that's the synthetic approach. What's called the synthetic approach. And therefore, what we're doing is an example of what is called synthetic homotopy theory. We're not depending on analysis. So what's interesting is that, as you'll see with Dan Licata's developments, is that we're able to develop quite a chunk of, well, I think, elementary homotopy theory, but non-trivial chunk of elementary homotopy theory, and yet nowhere in there is there anything to do with the real numbers. There's nothing, there's no definition of what a topological space is. There's no idea of what a continuous function is. It's all intrinsic in the type theory. And that's the very important thing. So another way I'm saying it is, it's what type theory is capturing. It's an intrinsic view. I don't know any better way to say it, or it's a synthetic view, that we abstract away from that. There are many instances of homotopy theory, not limited to topological spaces and continuous mappings, but in actually other kinds of structures. Similar notions of path arise and preservation of path. And type theory is the abstract theory of that. So that's what's going on. So it's good computer science in a way. Like, from a computer science point of view, identifying this as an abstract type and identifying the principle of path induction is what comes extremely naturally to us. That's our legacy from type theory functional programming for decades. And as a matter of fact, as it turns out, the mathematicians never noticed this, okay? Because it's just not like the mindset. It's just like they're not the way it is. So the thing that has made these advances possible is a marriage of well understood mathematical ideas and well understood computing ideas, and realizing that they each informs the other. So that is kind of what has happened over the last couple of years, is a recognition of this fact. So I like to view it this way, because the way we work here with functional programming and so on is very natural from a computer science point of view. Okay, that's the idea. Okay, so I'm supposed to be, in my mind, I'm supposed to be convincing you that everything we're doing is just functional programming. And indeed, what you're going to see is when Dan takes over, I've set him up, right? My whole week has been spent setting up the groundwork so that he can pick off some really amazing cherries. So you will enjoy some delicious arguments coming up, where you will see that something that could be written out as sort of math is really just very conventional functional programming techniques. And they are new proofs of results in homotopy theory that never were given before, because that functional programming mindset was never brought to bear on the problem. And so, and it's gone the other way as well, but it's both. You know?
So we're talking about, this is functoriality.
Yeah, I'm gonna prove this now.
Yeah, I was just about to ask, like, so.
I'm gonna prove it. Yeah.
In the models, we're talking about this as like weak functors.
Yes.
Strict functors.
Yes, exactly. Well, I'm going to explain what this means in a minute. Okay, but yes, now I'm going to explain it. Okay, so here's the thing that I'm going to get at. So this is going to be a theorem. Okay, this is not like an axiom. This is going to be a theorem. Okay, this will be a theorem. Okay, and I'm going to do this. I'm going to do that argument right now. The idea is, but here's what I want to get at, because this is a subtle point. For this to be a theorem means that it's implicit in the concept of path induction that everything respects paths. That is kind of non-obvious, okay? Another way to say it is, this is just like by way of conveying intuitions, the reason that path induction is valid is because everything that is definable in type theory automatically respects the path structure. There's no way to write down a function in type theory that would fail to satisfy this requirement. It's a little bit like saying, and it's also true about type theory, that every function we can write down in type theory can be interpreted into topological spaces, and all the functions you can write down are automatically continuous. There's no way to write down a discontinuous function. And let me give you an intuition about that. This is not a proof of anything, but I think it's a useful intuition. If you think about your freshman calculus or whatever, and the idea of a discontinuous function, how is that the example always defined? It's always defined by saying, oh, I have a function which is like maybe 0 up until 1, and then from 1 it becomes 1. It's a stair-step function. There's a case analysis there at that point where you say the argument is either less than or equal to 1 or greater than 1. And if it's less than or equal to 1, the answer is 0. If it's greater than 1, the answer is 1, and that's a discontinuity. The function jumps from there. Well, if you think about this from a functional programming point of view, how are you going to write that code? Because there's no way for a real number you can tell me, for a general real number, is it less than or equal to 1 or not? Okay, it's not possible. Why? You can think about this. This can be proved, but you can think about it intuitively in many ways. One is just think about decimal expansions. You're seeing 0.999999999, and as long as you've looked, you've seen all 9s, but for all you know, it's just about to veer off and say 8. But then again, it might just continue with those 9s, and so that's 1. So you see, there's no way, this is the informal argument, but there's no way to make the decision. What it means is, let's put it this way, the fact that type theory is constructive is what prevents you from defining the discontinuous function. Now, what I argued is not a proof of that fact, but it's a heuristic guide, right? Is that you kind of have the feeling to define something discontinuous, you're going to need to make a trichotomous decision at some point, okay? Constructive math denies that. You don't get for free the decidability. So in the case of real numbers, you don't get trichotomy. If you don't have trichotomy, because there's no program you can write to calculate, to make the decision, then you're not going to be able to write down discontinuous functions. That's the heuristic argument. It's not a proof, okay, but that's what's going on. The same thing is happening here. In type theory, everything I write down is good constructive math. Because it's good constructive math, everything will respect paths. And because everything will respect paths, I can do synthetic homotopy theory. That's it in a nutshell. Okay? This is the great thing. So think about this. It means that constructivity, which is motivated by considerations of computability, in my mind is a fundamentally computer science notion. Constructivity is absolutely essential to getting a clean account of dealing with